So thank you all for joining us after the holiday break. So I'm going to hand over to Brian to introduce the speaker.
Okay, so Happy New Year to everyone, and thank you for joining for today's colloquium. So it's a pleasure for me to introduce today's speaker, Lars Mohrmann. So just a quick report on Lars's career trajectory. So Lars got his PhD from Daisy Zeuthen and Humboldt University in Berlin in 2015, working on the characterization of cosmic neutrino sources. After his time there, he moved to Erlangen at ICAP, where he continued his work in astroparticle physics, but now moving into H.E.S.S, where he stayed until 2021 when he moved here to Heidelberg, where he led the H.E.S, the local H.E.S MPIK group. And last year, at the end of last year, he took over as the director of the H.E.S experiment. So a very prestigious role. So today he's going to tell us all about how H.E.S works, exploring the universe with high energy gamma rays using the H.E.S instrument. So I'll hand it over to you, Lars.
Thank you, Brian, for the introduction. Yeah, it's a pleasure to be here and talk to you about exploring the universe with high energy gamma rays using H.E.S. So this is the outline of my presentation. I'll have a short introduction, explaining a bit sort of the why and the how we do science with H.E.S, and then I will go into some results, give a short overview, and then I want to go into a bit more detail on like this. Is it better? Okay. Into these topics, so young massive star clusters, microquasars. Maybe I have some time to spend on the Crab Nebula, and then there'll be a brief outlook. Okay, so let's get started. This is the electromagnetic spectrum, which all of you know extends over many decades, and you can express it in terms of the photon wavelength or the photon frequency, or even the photon energy. In any case, if you look at sort of the visible light, which we see with our eyes, it's important to realize that this is only a very tiny fraction of the spectrum. And you can look at the sky in visible light. And here's, for instance, an image of a famous object, the Crab Nebula, in the optical. But of course, you miss a lot if you only look at these frequencies. And typically, you can learn a lot more if you look also at other frequencies or energies. And that's shown here. So here's a couple of other images of the same object, the Crab Nebula, in the radio, the infrared, the UV, in X-rays, and also at gamma rays. Now, the energy range that I will be talking about in this presentation is here. So I'll be talking sort of about the highest energy photons that we receive from the universe. So we're here roughly in this energy range between 10 to the 12 and 10 to the 15 electron volts. So this is tera electron volts, or TeV. Okay, so why would we be doing TeV gamma ray astronomy? So the main point here is that those gamma rays are produced non-thermally. Nothing in the universe is basically hot enough to produce such high energetic particles. And there's mainly two mechanisms by which they're produced. One of them is called inverse Compton scattering. So here you start out with a high energy cosmic ray electron that then upscatters a low energy background photon to a gamma ray. And that's how you get your gamma ray. And then the other mode is what we call hadronic production. In this case, you start out with a high energy atomic nucleus, a proton, say, which interacts with some ambient matter, say in a gas cloud, and then in the particle shower that then follows, gamma rays are produced. So in both of these cases, we start out with high energy charged particles. We call those cosmic rays. And so the bottom line is that we can use gamma rays to study the acceleration and the sources of those cosmic rays. Now, why is that interesting? So if we look at the energy spectrum of cosmic rays as we measure it here on Earth, that's shown in this plot on the right here, then, well, the first thing to take away from that is that, well, the universe is capable of accelerating cosmic rays to really unimaginably high energies, much higher energies than we are able to accelerate particles to here on Earth. Finding their origin is really a more than 100-year-old quest in astroparticle physics. Why is that so difficult? The reason is that I mentioned cosmic rays are charged particles, so that means they're deflected in cosmic magnetic fields, and we can't sort of infer their sources because we don't know where they're coming from. Now, a solution to that is to use neutral particles, neutral messengers, and this can be photons, neutrinos, or gravitational waves, for instance. The neutrinos and gravitational waves are pretty difficult to detect. It's a bit easier with photons, and so that means then high energy gamma rays. So that's what we're doing with H.E.S.S. Now, how do we go about detecting these gamma rays? Now, one option would be that you go to space and put a satellite. That's, for instance, what this Fermi-LAT satellite is doing, which measures gamma rays, but at slightly lower energies. So, say at giga-electron-volt energies, GeV. And the issue is that high-energy gamma rays become scarcer and scarcer as you go up in energy. So that's shown as an example here. This is the spectrum of the Crab Nebula, which is one of the brightest steady sources on the gamma ray sky. And you can see, so measured with this instrument, and you can see if you go to energies close to a TeV, you get maybe a handful of photons per square meter and year, and a square meter is basically as big as you can build a satellite, and so you just run out of statistics. So if you want to do TeV astronomy, that's basically impossible from space, and you need to do it from the ground. Now, to understand how we can do it from the ground, we need to first look at what happens if a gamma ray reaches us here on Earth, because it doesn't reach the ground. Instead, it will interact somewhere high up in the atmosphere, say at 20 kilometers altitude, and launch what we call an extensive air shower. So that's a particle cascade that develops through the atmosphere, and the number of particles in that shower will be proportional to the energy of the primary gamma ray, as indicated in this plot here. And the axis of this shower will be very closely aligned with the incoming direction of the gamma ray. So that means if we are able to observe that air shower, we can indirectly infer properties of the primary gamma ray. So that's the task then, to observe this particle shower. And there's two main ways of doing that. One way, relatively straightforward, is you just try to measure those particles as they reach the ground. So that's the approach of ground-level particle detector arrays. In this example, this is done using these so-called water Cherenkov tanks, where the particles go through the water in the tank, they emit Cherenkov light, and you detect that. If you want to be sensitive sort of in the TeV energy regime, you need to go relatively high up on a mountain to do this, so something like above 4 kilometers altitude, because otherwise the shower will have died out before it reaches the ground. So the main advantages of this approach is that you have a very large instantaneous field of view. You basically observe everything that's overhead at any given moment, and you can operate such an array basically 100% of the time. So that's nice, and you can gather lots of statistics on many sources at the same time. The disadvantages are that when you talk about sort of the resolution, how well can you reconstruct the properties of this air shower? It's let's say only modest, That's because you basically only measure the footprint of that shower and not its full development. And to cover a large area, obviously, you need to build quite a lot of detectors to cover that. Now, this is not what we do with H.E.S.S. There's another way, and that has to do with the Cherenkov radiation that's created by the secondary particles in that air shower. So let's have a look at this. So there's many charged particles in such an air shower, of course, and because those are highly relativistic, they travel faster than the local speed of light, they emit Cherenkov light. That's shown here, and just give you some order of magnitude numbers. For a 1 TeV gamma ray shower, this will have its shower maximum at an altitude of maybe 10 kilometers or so, and you have about 1,000 charged particles in that shower. And they emit Cherenkov radiation, which is strongly beamed forward, so the opening angle is about a degree or so, and you get something like 10 photons per meter of travel path and particle. And so that Cherenkov light then eventually reaches the ground and makes a light pool with a radius of about 100 meters or so, and you get a density of around 1,000 photons per square meter. So that's what you then have to collect and detect. And sort of the total integrated duration of the signal is pretty short because, well, the shower develops very fast. So this is of the order of, well, less than 10 nanoseconds or so. So this is the idea. You try and detect this Cherenkov light, which is again illustrated in the sketch here. And the way to do that is that you build what we call imaging atmospheric Cherenkov telescopes. So these need to have quite large mirrors to collect enough of these photons, these Cherenkov photons. And then they reflect the Cherenkov photons into a camera, and that needs to be a very fast camera to capture this very short duration Cherenkov light flash. Now with this technique, you get a somewhat higher resolution. Now sort of astronomers from other wavelengths will laugh at me, but what we call high resolution is something like a resolution on the direction of, say, 0.1 degree or slightly better. So that's still pretty bad for the typical astronomer, but with this approach, because we observe so indirectly, it's actually fairly good. You also get a relatively high instantaneous sensitivity because you have such a large collection area. Of course, this approach also comes with some disadvantages. It only works when it's dark, because otherwise you can't record that light flash. So you're restricted to dark and mostly moonless nights, which gives you a duty cycle of maybe 15%. And you have to point these telescopes. They have a field of view of maybe 5 by 5 degrees. So you need to figure out what to look at and can't observe many sources at the same time. Okay, and so this is the approach that we follow with H.E.S.S. So this is the experiment that I'll be talking about. H.E.S.S is for High Energy Stereoscopic System. It's located in Namibia and consists of 5 telescopes in total. 4 smaller ones, but well, they still have a 12-meter diameter mirror, so they're not actually small. So these are placed 120 meters apart from each other, and in the center there is one larger telescope with a 28-meter diameter mirror that was added a couple of years later in 2012. The other ones are in operation since 2004, so more than 20 years now. And with this array, we're sensitive to gamma rays in the energy range roughly 100 GeV to 100 TeV. Okay, maybe just to answer some questions that you might have. Why does it help to have multiple telescopes? So you saw we have 5 with H.E.S.S. The answer is that if you do stereoscopy, which is also where the name High Energy Stereoscopic System comes from. Basically, you have more information. You observe the shower from different sides, and you can better reconstruct the properties. This is also illustrated in this sketch here. So basically, from the image of one given telescope, you would only be able to say that the incoming direction is somewhere along the major axis of this ellipse. But if you have multiple views, you can reconstruct the direction and hence also the energy much better. You might also ask yourself, why does it help to have telescopes of different sizes, as we do in H.E.S.S, for instance? Now the answer to that is that the size of the telescope dish that you put basically determines your minimum detectable gamma ray energy. Because it determines how much of these Cherenkov photons you can collect. So that's the main driver for the low energy sensitivity. Whereas the total instrumented area basically on the ground is what determines how many of these extensive air showers you will be able to detect. So it's the main driver for the high energy sensitivity. So if you want to have low energy sensitivity, you build a big telescope. If you want to have high energy sensitivity, you build many small telescopes and spread them over a larger area. And if you want to cover an energy range that's as large as possible, basically, then you put telescopes of different sizes. Okay. Good. So then let's have a look at where H.E.S.S is in the landscape of gamma ray observatories across the world. So we have a map of the world here, and H.E.S.S is located down here in Namibia, as I said. Now there's two other arrays of Cherenkov telescopes that are operating currently, which are MAGIC on the island of La Palma and Veritas in the US. So these also consist of several telescopes, and they apply the same technique as H.E.S.S, and they also have been measuring since many years. Then we also have observatories that use this other concept, the ground level particle detectors. And so here the two main arrays are HAWK in Mexico and LASO in China. So these are, as of today, sort of the main gamma ray observatories in the TV energy domain and above. And you will notice one thing immediately. H.E.S.S is the only experiment that's on the Southern Hemisphere. All the other ones are in the north. And that's actually important because from the Southern Hemisphere, you have a much better view of the inner galaxy. And so that's sort of one unique selling point of H.E.S.S. And naturally, future experiments will be trying to go south as well. So the next generation array of Cherenkov telescopes is going to be CTAO, or the Cherenkov Telescope Array Observatory, which will consist of even more telescopes than H.E.S.S to achieve an even better sensitivity, of course. This is actually planned to be built on two sites, or is currently being constructed on two sites. One in the north, also in La Palma, and one in the south in the Atacama Desert in Chile. Okay, and then we also have plans for ground level particle detector arrays in the south. And I mentioned two here. One of them is called Alpaca in Bolivia. There's a prototype of this currently under construction. This is not bigger than HAWK or LASO, and it will really only be sensitive above, let's say, tens of TeV, so really high energies. And then there is SWGO, which is still in the planning phase, but they also want to put a prototype soon. And this is actually planned to be larger and planned to surpass HAWK or LASO in sensitivity. But it's in an earlier stage compared to, for instance, CTAO. Okay, now to put all of this a little bit into perspective and understand what the role of H.E.S.S still is today, it helps to look at sensitivity and angular resolution curves, which are shown here. So that the plot on the top here shows the essentially the flux of gamma rays from a point-like source that's required to detect that source with 5 sigma significance in a given amount of time. And you can see the current generation IACTs, of which H.E.S.S is one, in dark blue here. CTAO will be, well, about an order of magnitude better, and is down here. And then you have the ground level particle detector arrays like HAWK or SWGO and LASSO. And you can see that those achieve better sensitivities at the highest energies. So say above 10 TeV or so roughly, they surpass the Cherenkov telescopes. However, if you look at the angular resolution, which is shown here, again, as a function of energy, you can see that these ground level particle detector arrays achieve a worse angular resolution. So if you want to do some detailed morphological studies, resolve the sources spatially, then that's where you will need IACTs. And the same is true for, mostly true for short time transient events like gamma ray bursts, novae, AGN flares, where it also helps to have the IACTs. Okay, good. So with that, I would like to then move to the science that we do with H.E.S.S, and this slide is supposed to give you sort of a panorama of different results. These are all, so these plots are all coming from publications from the last couple of years. And you can see we can do many things with this instrument. We study extragalactic sources, many active galactic nuclei. We are searching for gamma ray emission from gamma ray bursts and have successfully done so, as I will show in a minute. Or we, for instance, also study the extragalactic background light. Then we have a large variety of sources that we study in our own galaxy. Some of them we know and study since long. Supernova remnants, pulsar nebula, the galactic center as well, or binaries are sort of in our program since long. But there's also sort of a few newcomers that we sort of came up during the last couple of years, and that turned out to be very interesting. Star clusters, microquasars, or novae, for instance. And then there's also other things we can do, for instance, measuring the electron spectrum or searching for dark matter. Now, I will talk in more detail in my presentation about star clusters and microquasars, maybe pulsar nebulae. But before I go into that, I'd just like to sort of flash 3 of those results here very briefly, just to give you a flavor of what different kinds of science we are able to do with H.E.S.S. And the first one is this one, which is about the discovery of a new radiation component from the Vela pulsar, reaching 20 TeV. So here we're talking about pulsed emission. So this is radiation that reaches us sort of modulated with the period of the pulsar, fast spinning neutron star. So pulsars typically are detected in the radio domain, and for a couple of hundred of them, we also know that they emit gamma radiation, and this is usually in the GeV domain. So the typical energy spectrum from a pulsar looks like this, as shown in the plot here, measured with Fermi. So it has a peak at several GeV, and then there is a sharp drop, and the flux goes down very steeply. Really the only exception so far until recently was the Crab pulsar, which is shown in light gray here, which sort of had a tail here, a power law-like tail, extending really into the TeV domain, which allowed its detection also with IACTs. But this picture has now changed quite dramatically, because recently we were able to discover a new component in the emission from the Vela pulsar, which is shown in blue here, and you can see that is really clearly a sort of distinct spectral component in this radiation, reaching energies of up to 20 TeV, which was really not predicted, and puts severe constraints on the theoretical models. The plot on the right here shows the phasogram, so that's the arrival times of the photons modulated with the period of the pulsar. In the GeV domain down here, this is then sort of measured with H.E.S.S, basically the measurement with shown in green here, at slightly high energies, and then above 5 TeV, you see we have sort of not many photons, but still we get a significant peak here, as shown. Okay, so that was the Vela pulsar. Another result I would like to highlight briefly is a high statistics measurement of the cosmic ray electron spectrum. So now we're actually not looking at gamma rays, but at electrons. And we can do that because, well, an air shower initiated by an electron is also an electromagnetic air shower. It looks very similar to a gamma ray initiated air shower. And so if we look into regions of the sky where there's no gamma rays, then we can try to attempt a measurement of the electron spectrum, cosmic ray electron spectrum. The electrons are still much less numerous than cosmic ray protons, however, for instance. And so what's needed to do this is a very strong rejection of the background of, let's say, proton-initiated air showers. So you can see an illustration of this down here. This is the distribution of some classifier that distinguishes between electrons and protons. The distribution for electrons is shown by this blue distribution, and then a model for the background is sort of this this dashed line here, and the two combined then give you a distribution like this. And from the height of this peak, you can try to infer how many electrons there are in your data set. And as you go up in energy, that peak becomes smaller and smaller. And then, you can try to derive this spectrum. Here, this is basically a classifier that distinguishes how much an event looks like an electron or a background event, an air shower initiated by a proton, let's say. So the further you are on the left, the more it looks like an electron-initiated air shower. Okay. So we were able to do this measurement of the electron spectrum, and you can see that sort of it extends now much further than what you can measure with direct satellite experiments. So we're able to probe an energy range here, where experiments like AMS or CALAT just run out of statistics. So that's very nice. We were able to confirm sort of this break at around the TeV here. Also another interesting thing is that we don't see any upturn of the spectrum at high energies, which is something that you might expect if you have some local nearby source of electrons and positrons. Okay. And then one last sort of flash result, which is the detection of a gamma ray burst afterglow up to 56 hours after the burst. So gamma ray bursts is something that we have been searching for with IACTs since very long, since the beginning basically. For a very long time that was unsuccessful until in 2018 we were able to detect really our first GRB. And then just a year after we got lucky a second time. So that's the GRB 1908-29A. And this one happened to be extremely nearby at a redshift of only 0.08 or so, which means it was very bright for us. And we were actually able to detect the afterglow emission from this gamma ray burst in 3 consecutive nights, as you can see in the light curve here. So this is the first night, second night, and the third night. And if you compare the gamma ray measurements with the X-ray signal, so that's shown in blue here, you get the same temporal decay, and the spectrum is also very similar, and that turns out to be very difficult to model with sort of your standard model for such GRBs, which is a synchrotron self-Compton model, and that was in this case challenged by our observations. Okay, so that just to give you sort of a some flavor of the science that we do. And now there's some topics that I want to go into deeper, and one of them is young massive star clusters. What are these? As the name suggests, they're clusters of massive stars, so typically OB stars or also Wolf-Rayet stars, with total masses of, say, 10 to the 4 solar masses or so. And if they're very compact, then these stars can be sort of as close together as a few parsecs. So it's really very extreme environments. And those massive stars have very strong winds. You can have supernovae. And then what you get is sort of a collective wind from such a star cluster, which can blow what we call a superbubble into the interstellar medium. There's two sort of very well-known star clusters shown here, H.E.S.S and R136, and I'll come back to these later. Now, why are these interesting? Well, you can imagine if you have so many stars with massive winds packed so closely together, you inject a lot of energy, and so these are really nice environments for particle acceleration in principle, and several sort of theories have been put forward here. Various places where the particle acceleration could happen. One possibility, for instance, is this termination shock of the collective cluster wind that you expect to form if you have a compact cluster. Okay, and so then first publication that I want to talk about is this one that we published a couple of years ago. So this is targeting this massive star cluster H.E.S.S. We start with this map here, and I'll walk you through what you can see here. So this black star in the center, this is where the star cluster is. H.E.S.S is the most massive young star cluster that we know of in our galaxy, with a total mass of around 10 to the 5 solar masses. And this is all packed into a radius of, as I said, just a few parsecs. So the extent of the star cluster is really not bigger than this star symbol on this plot here. Okay, so it's very compact. And then what's shown here inside this dashed line is a gamma ray source. So this is a gamma ray flux map here above energies of 0.37 TeV. And we call this source H.J1646 minus 458. And as you can see, it's very largely extended. Okay, it's very big, and we think, nevertheless, that it is associated with this star cluster. So let's have a look at this source in a bit more detail. It's very extended, so it's about 140 parsecs or so across, so 100 times larger than the cluster itself. It also shows a very interesting sort of spatial structure. In particular, you get something like a ring-like structure that I tried to indicate here, with the star cluster being close to the center of that ring. And so that's very intriguing. We also checked if that looks the same at different energies. So here's another map now above 1 TeV. You can see you can still make out such a ring structure and several bright spots along that ring. And even above 5 TeV, the picture still looks rather similar. This is also confirmed if instead you just look at basically a radial profile of the emission. You get this peak here at the distance of about 35 parsec, and that is true basically at all energies. Now looking at the energy spectrum of the emission, we extracted that in 16 different sort of small regions across the source. However, finding that the spectrum actually looks remarkably similar in all of these regions. So this plot here shows this measured spectral index in each of these regions. and it's basically compatible with the same spectrum everywhere. So we can basically just add up all of the regions, and then we get this spectrum here, which is then the combined spectrum for the entire source. And you can see that that reaches to energies of close to 100 TeV. So this is really quite a powerful accelerator. So then we try to understand where's that emission coming from, and we try to correlate it with tracers of gas, because that would be target material for the cosmic rays to interact with. However, if you look at these maps, which show atomic hydrogen and molecular hydrogen tracers, you can see that wherever there's bright gamma ray emission, shown by the red contours, there's very little gas. So we have a low gas density. Now, concerning the site of the particle acceleration, one interesting thing is that if you look at this ring-like structure that I mentioned earlier, and then try to estimate what would be the radius of, or the position of this termination shock of the collective cluster wind, and you make some basic assumption about the star cluster, you come up with around 30 parsec or so. And so that's very close to the radius of this ring-like structure that we have been observing, meaning this could be an indication that the particle acceleration is happening at that termination shock, and that would be a first demonstration of such a thing. In that scenario, it's preferred that the origin of the emission would be leptonic, so we have this inverse Compton mechanism that I introduced in the beginning, which and that's also mostly because for the hadronic scenario you would actually need some target material which isn't there. This, however, doesn't mean that there are no hadronic cosmic rays, that there are no protons being accelerated. We just don't see them because there's no target material. Okay, this is basically just summarizing what I just said. This is, this star cluster turns out to be a very powerful cosmic ray accelerator. We observe this ring-like structure, and because of the low gas densities, we think the emission that we see is mostly leptonic. Okay. Now, one question was left unanswered in that study, and that is what's actually causing this bulge here that sort of protrudes out of this ring-like structure. And here I want to just do a quick detour on a study that isn't a H.E.S.S study, but it's still very interesting, and it was sort of a spin-off of this earlier work, and that was just published very recently. So here we now looked at the same region at somewhat lower energies with the Fermi-LAT in the energy range from 3 GeV to 3 TeV. Now, just to begin with, this is again the TeV emission that I just showed you earlier in the other plot. You have to tilt your head a bit because this map is now in galactic coordinates and the other one was in equatorial. So this bulge is now down here, okay? And what we found in this somewhat lower energy range is, again, a very extended emission region, but not where the TeV emission is, but offset from it towards the direction of this bulge, okay? Now, trying to model that emission, first thing you can do is try to look in the catalog that's provided by Fermi-LAT. In that catalog, this whole emission region is modeled with 2 extended and 6 different point-like sources, so it's all a big mess, basically. But it turns out you can actually come up with a much easier model, which is just one Gaussian component down here for this bright source here that we now call J1654, and then another component up here where we use basically a template derived from the TeV emission in the fit. And that's statistically preferred very strongly over this model from the Fermi catalog. Right, just for future reference, we divided this region down here into 2 regions, one near to the plane and one far. And so what you can see, this source here, it seems to be connected somehow smoothly to the TeV emission up here. And so the question is that we asked ourselves, could this be actually connected to Western 1? Could this be cosmic rays traveling down here and producing this emission down here? And now what we did next then is to look at gas maps. And this is a little bit difficult to do because it turns out that the velocity of the gas near the star cluster is not well constrained. So that's why we're showing maps in two different velocity intervals that corresponds to two different distances to the cluster here. In any case, you can see basically what you observe in both of these maps. You can see it a bit better in the left map, that there is an underdensity here where we see that GV source compared to neighboring lines of sight. And if you compute sort of what the difference is, you end up with something like 0.7 to 1.5 times 10 to the 20 per square centimeter in terms of the H1 column density. And so that then got us thinking, is that maybe a cavity that was created by an outflow of particles from the star cluster region? And we try to work that out if it's sort of feasible. And if you do that, you find that the requirement, basically the energy requirement to form that cavity is something like 10 to the 50 or so erg, which is well within the energy budget that it's provided by the wind of this star cluster, which is a very powerful star cluster, as I said. And so that's basically then the model that we propose. So you have the superbubble around the star cluster, which is expanding asymmetrically because of the density gradient. Yeah, you have the galactic plane up here where densities are high and then densities decrease as you go down. And so this superbubble expands in this direction away from the plane. The cosmic rays are accelerated up here where the cluster is. The high energy electrons, they lose their energy very quickly. So you see the TeV emission up here. But the lower energy electrons, they have longer cooling times. And so they are transported with this outflow down here and would produce the GeV emission somewhere down here. If you do a simple modeling, you find that the energy density of the electrons in this outflow is of the order of 1 to 10 electron volts per cubic centimeter, so that's quite substantial. And it implies that because there's no reason to expect that only electrons would be accelerated at this shock, you would expect that protons are accelerated as well, typically with a higher efficiency. And so from that, you would infer that the energy density of protons is actually is even higher in this outflow. And so that means what we're observing here is an outflow that's loaded with cosmic rays. So cosmic rays are transported with this outflow away from the plane. And eventually, this, we think, would open a channel for cosmic ray transport from the plane into the galactic halo. So that's quite an interesting result. Now, Brian, where do I stand with time? Yeah? Okay, then I will skip this one and talk about this result, which is now about microquasars. Okay, so the object we're looking at is this one. This is the so-called Manatee Nebula, and it's called like that because it looks like the big sea animal. It's pretty big on the sky, about 4 full moons wide. Now, what is this? This is the same image, just tilted. And this is the leftover of a supernova remnant, which is maybe about 20,000 years old. And the blue stuff you see here is radio emission, so it's not actually visible to the naked eye. And this is synchrotron radiation from relativistic electrons. And what sits in the center of that system is what we call a microquasar. This is basically the leftover of that supernova explosion. And it's a binary system. So you have a black hole that's and a companion star, which is a supergiant. And the black hole accretes matter from the supergiant and then launches two jets, where material is then transported along these jets, and these are highly relativistic. Now you can look at the system in X-rays, and then that's shown by the white contours here, and then you see you have high X-ray emission close to this microquasar, then it disappears somehow, and then you observe these large-scale features here, which again are sort of due to these jets, and they tell us that there are highly energetic electrons must be present somewhere in these large-scale jets. So they must be, they must be coming from somewhere, these high-energy electrons, and the question is where, because just from this measurement we don't know where are those electrons accelerated, and why is it that the jets disappear and then reappear at quite a large distance, 25 parsecs or so from the center. And this is where the H.E.S.S measurement then comes in. So with H.E.S.S we were able to also measure TeV gamma ray emission from those jets, as you can see here. And not only that, we also looked at this as a function of energy. So we studied the spatial structure of the gamma ray emission in different energy bands, which is shown here in 3 different bands. And if you look at this, you can see it better if you look at the upper jet. You can see that sort of the peak of the emission is at low energies further down the jet, and then it moves basically to the base of these large-scale jets here. And you can see a similar thing if you make a profile of the emission. You can see that sort of this peak moves inwards towards the direction of the microquasar. And so this means, or from this we conclude that the electrons, they must be accelerated here, where sort of we see the high energy emission. And then these electrons are advected along the flow of the jets, and we can actually determine the velocity of the flow from this measurement here, and then they sort of start to lose their energy, and when they have low energies, we observe them further along the jet here. So that was a very interesting result, which is again summarized here in this nice picture, where you see the microquasar in the center, and then these places where we think the particle acceleration takes place at some kind of shock that must be forming there, and then the electrons move outward. And then maybe I can quickly say a few words about another microquasar, and this is a very recent result. This paper just got accepted. This one is called V4641 Sagittarius, and this is another microquasar, so a system where you have a black hole that's supposed to exert jets. As I said, it's off the plane, so at a galactic latitude of -5 degrees. And until recently, it wasn't deemed very remarkable until it was detected first with HAWK in an energy range of 18 to 217 TeV. You can see maps here, and a spectrum. So the spectrum of the emission is relatively hard, spectral index of -2.2. With their measurement, they weren't really able to say if this is just one sort of elongated component or maybe 2 point-like components. This is because of this sort of relatively bad angular resolution that's provided by these kinds of instruments. And then sort of the other ground-level particle detector array, LASO was able to do or to measure emission from this object as well, reaching even higher energies. So now we're talking about 40 to 800 TeV of energy, and a measurement of the spectrum here. At these energies, the index is a bit softer, However, again, they couldn't really constrain the morphology of this emission properly. But this is now where H.E.S.S can really contribute. So we looked at this source as well, which we hadn't done before because it's relatively far off the plane. In an energy range somewhat lower, 0.8 to 22 TeV. However, we were now able to sort of find a slight preference for two separate components, which could indicate again that you have two separate jets where particle acceleration could be happening. And we were also able to spatially resolve these two components. So they're not point-like. Each of these components is spatially extended. And if you now look at this sort of broadband spectral energy distribution, that's shown here. The red points are from H.E.S.S, and then we have V46, 41, then we have the Hawk and the lasso points here. And so now you can see this distribution has a peak at around 100 TeV or so. So that's really the first kind of source where we see something like that, and really implies this is an extremely powerful particle accelerator, and a very, very interesting system to study. We tried to look again for energy-dependent morphology like we did for SS433 earlier, which we don't really see if we just look at H.E.S.S data alone. This is lower energies, this is higher energies, kind of looks the same. If you start to compare it also with the Hawk data, that's shown in the lower plots here, you sort of see some differences here and here, but it's really not very conclusive at this point. Again, we looked for ambient gas as target material, but the densities are very low because this is an off-plane source. We did some modeling, and again, the bottom line is that for this system, a leptonic model is strongly preferred because there is essentially no target material for the cosmic rays to interact with. In this leptonic model, which is shown on the left-hand side here, we find that the magnetic field in this system must be relatively low, and the electrons must have been injected fairly recently. And you need velocities of this jet that are sort of mildly relativistic. Okay. Okay, then I think time is up. Okay, then I will also not go into this one. That's fine. And just give a very short outlook on H.E.S.S. So we will continue operating until at least September 28th. That's sort of what's currently agreed on. And we have an exciting legacy program set in place for the still 3 years. One strong focus is time domain science, which I didn't talk a lot about today. So GRBs, for instance, novae, AGN flares. But we also will be doing promising campaigns on, for instance, microquasars, star clusters, also binaries. Beyond 2028, situation currently is unclear, let's say. We will have to see. But already we are making sort of some plans for what to do with the more than 20 years of H.E.S.S data that we have recorded by now. And the aim is that we want to sort of prepare an archive for these H.E.S.S data that would eventually be made public for the community. You could analyze these data with the same tools that you will, or that one can use to analyze data from CTAO. Preparing this will be a huge effort for the calibration, and so we actually need to start this effort now, but hopefully it will be a very valuable legacy for the community. And with that, I close and thank for your attention.
Then and I'm not going to throw from the bottom all the way to the top. Yeah.
Yeah, I have a question concerning the acceleration efficiency. So you showed for Westerlund 1 that you expect the acceleration efficiency for protons to be higher than the electrons, but what about the numbers? Can you confirm, or can you pin down a number for the acceleration efficiency based on the cluster content you have and the emission? So the classical number we have in mind is like 10% of the energy is converted to cosmic rays, but can you want to be okay 10%, or is it more 1%, or is that all too far reaching?
No, so we tried to do that exercise, at least looking at the TeV emission with H.E.S.S. And if I remember correctly, for the hadronic models, we were in that ballpark of 10% or so for the hadronic model, yeah. And similarly for the leptonic model, of course it's much lower, but it's also in principle feasible in terms of the energetics. Yeah.
Come in.
Okay, it works. So thanks for this great overview of what H.E.S.S has done and what it can do for us. I was
Well, I mean, during the day, there's nothing we can do with the telescopes, really.
sure. Okay.
So
It includes day. This is not just night.
no. So the 15% is sort of all the time, yeah. So the 85% includes daytime, where yeah, obviously you can't really observe. We are able since a couple of years to observe at least under partial moonlight with sort of adapted trigger settings and so on, which increased the duty cycle a little bit. And yeah, so in the times when it's too bright, typically we cannot do much. What some people have been pursuing a while back is intensity interferometry, which is observations of stars and looking for correlations in the arrival times of optical photons, with a dedicated setup that is mounted on the telescope. And this could be done at times when we couldn't do our normal gamma ray observations. But yeah, other than that,
Okay.
telescopes
Thank you.
are turned off.
The next question, maybe
Yeah.
We're gonna play with the toy.
Now I have to change the retune. Okay, I have a question about the microquasars. So thank you for giving us so much information about SS433 and the other.
Yeah.
Now I need to digest all of this information. But my question is about the take-home message. So they are two microquasars, but they are also two very different beasts. One is a very low mass black hole, the other one, the typical 10 solar mass black hole. The companion star is very different, a small one, few solar masses in one case, a big giant in the other. So, and there are also differences, as you showed from the gamma ray emission. What can we learn from those differences in their gamma ray emission about the way microquasars work?
Yeah, that's a very good question, and I'm afraid I probably don't have a very good answer yet, because, well, up to now we have these two systems that we measure with H.E.S.S. In this paper, actually, with LASSO, they observed very high energy gamma ray emission from a few more, but still the sample isn't very big. And yeah, I mean, a priori, for this system, B4641, you wouldn't have thought that would be such an efficient particle accelerator. It was also thought for a long time that you would only observe these systems when they undergo flares. And so people started really, oftentimes the observations would be done when a flare would happen, but it turns out that
This one is a transient.
no, it's not transient. So it turns out these are actually steady emitters. And the emission that we see is also coming from a much bigger region than previously anticipated. So we observe these large scale jets now, and we observe the emission to be steady and not transient, not just connected to flares, but it's always there. So this we have learned already, but really what makes a particular microquasar system a good particle accelerator or not, we don't really know yet. But yeah, as I said, we will be observing more, and maybe, yeah.
Can we say something also from those that you try to observe, but they didn't show any?
Potentially, yes. I mean, as I said previously, we often looked just at particular times when there would be a flare, yeah. Now it turns out that maybe we were looking in the wrong way, basically. But still, maybe we can learn something from the non-detections earlier. Yeah.
Okay, coming to you.
Yeah. Well, the cluster is parsec scale extended, but the gamma ray emission, let me go back. The gamma ray emission is on much larger scale. So let's go here. So this is 140 parsec. I don't really think that we expect to see any variations in time here. I mean, the lifetime of this cluster is 4 mega years or so. So it's been going on for a while.
Another one in the back. Okay, let's see. Watch out next to you. You got a laptop. Maybe I'll go midway. Can I go to you midway? All right.
Almost.
It doesn't work anymore.
I can speak up. To look for dark matter, so you mentioned that in the previous slide, but you didn't get into it, because I've read about this GeV excess to look for dark matter, but H.E.S. looks at much higher energy, so I'm just wondering how you look for dark matter in the energies that H.E.S. looks at.
Yeah. Well, I mean, the principle is very similar to like you would do it with Fermilab in the GeV range. You look for annihilation of dark